So hello guys, we are Team Yang of Digital Clock. I'm Tian Yuqing.
I'm 学习照。
I'm Xu
Okay, so next we'll discuss more details in the next session.
Okay, so let me briefly introduce our design review for our digital clock chip. Here is our chip block diagram. On the left and the right side is our PCB free flight devices like 7-segment display, buzzer, 3 LED, and we have 6 buttons like reset, mode, start, bit shift, bit plus, and bit minus. We also have the crystal oscillator on our PCB board, and we have 2 switches. One is for our power on, and another one is for our low power mode. In the middle of this block diagram, all this yellow block are our analog parts. We have all the drivers for display, for buzzer, and for LED. And we also have the level shifter, like shift from 1 volt to 2.5 volts, 2.5 volt domain to 1 volt domain. We also have the crystal circuits, and we have the anti-button design. So the anti-button design is using to avoid the case we press multiple buttons at the same time. And all other blocks are designed by standard ASIC floor using TSMC 65 nanometer CMOS technology. The overall process is including but not limited to like RTL simulation by Cortacin and Kinagenus to do logic synthesize, and also do port synthesize by Cortacin, and using Cadence Innovus to do automatically place route, to do import, to do floor plan, to do place, to do clock tree synthesize, to do automate optimizations, and to do route, to do export. And finally, we will do the timing analysis and to do physical design simulation and its corresponding DRC and LVS check. And next is our state transitions, or we can call it as our chip user menu. So basically, we have 3 important functionality mode: clock, showing our clock, showing the date, and showing the timers. For each functional mode, we have its corresponding time setting mode. We call it as memory clock, memory date, and memory timers. For each these 3 time setting modes, we can use 3 buttons to do the manually time corrections. And very specially, we also build up a MCU interface, so we can read the data from our Arduino board to do the MCU time correction automatically. Here is our chip pin map. So totally we have 64 pins, and 48 pins is for functionality, and another 16 pins is for our testing. Here is our timing summary. So you can see there's no any violations for our chip, and our chip density is around 30.7%. Yeah, and here's our generated layout of digital core, like the digital part from Cadence Innovus. And here is our total overall floor plan for our chip. Most importantly, we have our digital core, we have our like the head frame, and another is analog part like decap. We have a common castle display driver, we have a level shifter, we have buffers, and we have the buzzer and LED driver. And here is our test result. We read it from our oscilloscope. Power assumption and accuracy are 2 very important metrics for our design. And you can see in 2.5 volt domain, our power assumption is near 0.33 milliwatts, since all the power assumption is from the PC board, especially for the 7 segments. But if for 1 volt domain, like our digital core, the power consumption is just 36 milliwatts. And if we turn our low power mode on, our power consumption can be decreased from 0.3 milliwatts to 10 milliwatts. And the detail of our low power mode can be described in the following section. And for our accuracy, our chip accuracy has achieved only 0.2 seconds per hour. Yeah, and next session.
Hi, this is Xingyuan. I'm gonna introduce our analog part, include their schematic level, layout level, as well as their simulation result. The first part is the level shifter. We use 1 volt. We will shift up the 1 volt signal to the 2.5 volt signal. The 1 volt signal is generated from the digital core, and the 2.5 domains result will use to drive the driver off chip. Here is 4 MOSFET under the 1 volt base, and those are all the devices with the 6 device, which is used for 2.0 volt domain. The basic structure is here like this. We use cross-coupling MOSFET to shift up the 1 volt to 2.5 and keep 0 when the input is 0. I also added totally 4 inverter, 1 at the input and 3 at the output, in order to increase the driving capacitance of the device. And here is the simulation. We can see the transfer time from both the low to high or high to low are really fast. Because our clock signal is 30 microsecond, so the 60 nanosecond is very, very fast. Here is the layout for the level shifter. You can see we use multiple vias in order to prevent the filter of the single via. And here's the area of the level shifter. It's very, very small. Next is our 7-second LED part. This is one of the most important driver in our design, which consists of 2 parts. One is 1 hot, which consists of the NMOS. Another is segment enable, which is consists of PMOS. For our simulation, for our design, we first make sure the width to drive the enough current, and then adjust the width and finger to make sure the resistance is as small as possible. Here's the simulation. We can see the turn on and turn off time for the driver are very, very fast. And even though in the worst case, for the worst scenario, the transfer time is also very fast. So the design is robust. Here is the layout. Since the 1 hot, which is digital enabled, I need to pass higher current compared with a couple of times bigger current than the second enable. So we use the highest metal level, which is metal 9, for the connection. And for the second enable, we use metal 8. The widths are very high, almost 10 micrometer, in order to make sure the current can pass. Now here's the single LED. Single LED only needs to pass 5 microamp. So it's not such complex. We only need 1 NMOS for the driver. Here's the simulation result. Again, the transfer time is very, very fast. And also very fast in the worst scenario. Now here's the layout. You can see we still use metal 8 for the connection. For the metal here, our design gives them 2 times bigger for the current which it should pass. So this method is used to prevent the unexpected high pulse current burning the device. And next is the buzzer driver. For the buzzer driver, it has the same functionality as the single LED driver, but this time we need to make sure it can pass 90 milliamp. So here's the simulation. Again, the transfer time is very fast compared with our clock signal, clock frequency. And also the worst scenario. Here's the layout. At this time we use a metal 7, and I give them extra 10 milliamp at budget, so the metal should pass 100 milliamp at maximum. Next is our crystal circuit. Our crystal circuit has only one part on chip, which is a big inverter. The inverter structure is very simple, but I still designed large enough. And here is the sample, the layout. And for the connection, the input and output wire is very weak in order to allow the large current pass. The simulation. We use 100 picofarad as load this time. So even in this scenario, the worst case transfer time is still small enough, even though it's bigger compared with the previous one, but it's still small enough compared with our clock signal. And here is the input and output buffer. The input and output buffer just consists of two inverters connected with each other. So the structure are same between the input and output. The only difference is the input and output wire. For the input and output wire, we adjust the different metal in order to fit our pad frame. And by the way, for all of our layout design, we add a pad frame pad frame here. You can see the circle for both PMOS and NMOS. All of our design included that. This method is aiming to prevent the latch up from the circuit. And again, just as I mentioned before, we use multiple via here and here for whole of our design in order to prevent the future of the single via. Finally, is our decap. We have a lot of decap on our circuit, but here we use the NMOS-based device to consist of our decap and not the regular capacitor, because the NMOS-based decap has higher capacitance per array, which has higher capacitance efficiency. Here's a single decap, and here is the 10 times 10 decap array. Okay, here's all the part regarding to the analog and the layout. Thanks.
Okay, so here is our design of the digital clock. So we use 2 batteries to provide 3-volt voltage to power the whole system. And on this side we have 6 buttons as input, and for output we have 7-segment LEDs and a single LEDs and buzzers. And we used to have the crystal circuit on the PCB board, but unfortunately it doesn't work. So we use the 555 timer to generate a 32 kilohertz clock for our chip. So for our chip, we basically have 3 different modes: the clock mode, calendar mode, and timer mode. So by press the mode switch, it can switch between these 3 different modes, and the LEDs can indicate which mode you are in right now. So firstly is the clock mode. So you can see the time is counting up, and by press the setup button, so we can set the clock. So here I'm going to set the clock to 10 seconds, and once I press the start, it will start count up. And for the calendar mode, so also by press the setup, we can go to the we can set up the date. So here we have interesting function. So we know that there are 31 days in March, and once we change the month from March to February, so you can see the the day automatically change to 29, and also it can deal with the leap years, because we know like the 2000 is a leap year. So if we change the year from 2000 to 1999, so you can see the day can automatically adjust to 2028. Then is the timer mode. So also by press the setup, we can set up the timer. So here I'm going to set up a 5-second timer, and once I press the setup again, it will start countdown. So once it reaches to 0, there is a beep from the buzzer, and by press any button, we can stop the timer. So that's basically the 3 different modes for our chip. And also we design a low power mode, so because the most of the power is consumed by this 7-segment LED. So here we have a switch can disable the display, so it can save a lot of power, but this switch just disable the display, but the chip is still working. It means the time is still running. So you can see right now it's 15 seconds, and we turn off the display and wait for a few seconds and turn on again. So you can see, so the time is still running when I disable the display. And also we have the button debouncer and anti-button mode. So this can prevent a situation that somebody press several buttons at the same time. So for example, right now I press the setup and the mode switch at the same time. So you can see nothing will happen. So the chip will regard this as an invalid input. So basically that's all the functions we designed for our chip.
So finally, we sincerely appreciate for the generous sponsorship from Apple company, and we do appreciate for all the help from Professor Kinget and all the TA members. And we also have a special thanks for our TA Moshimichi, who gave us a very detailed guidance for all the process when we design our chip.